In this first clip, Bernardo jumps and extends his arms 3 meters above the ground. It is at this point where he applies force to accelerate the ball to 2 meters per second at a 60-degree angle to the horizontal. This means that if drawing a velocity triangle, the ball will have a horizontal velocity of cosine of 60 degrees times 1, which is 1, and a vertical velocity of sine of 60 times 1, which is approximately 1.732 meters per second. This means that Fernando hits the ball 3 meters above the ground at the end of the ball's path, which will be as far as its range, that is, the initial velocity squared times the sine of 2 theta divided by g, which is about 0.35 meters. In this next clip, one can see the concepts of projectile motion. As Raphael attempts to jump over barriers, one can see that he has enough initial velocity and an angle close to 45 degrees on his first jump to cross the barrier. However, he does not have these criteria for the second jump. His delta y is therefore inferior to the second barrier, and he fails.
In the next clip, Bernardo passes the ball to Fernando again, but at a 45-degree angle with a velocity of 1 meters per second. That means that the horizontal velocity and vertical velocity are the same. At sine of 45 times 1, which is about 0.707 meters per second. This time, Fernando hits the ball at a maximum height, which, plugging into the equation, velocity final squared equals velocity initial squared plus 2a delta y, with final velocity set at 0. The maximum height reached by the ball is 3 meters plus delta y, which is 3.255 meters above the ground. This is useful as a greater initial height enlarges range, giving Fernando a better chance to hit the ball over the net. The volleyballers jump before hitting the ball to hit it at a higher initial height to increase potential range. They have a greater range of angles to hit the ball at, along with greater velocity. They then can get the ball to land wherever they want it to.
Francois spikes the ball, accelerating it for 0.1 seconds from a velocity of -1 meters per second to 9 meters per second, meaning an acceleration of 100 meters per second squared on a 0.25 kilogram ball. This means he exerted 25 newtons of force onto the ball. Gravity is negligible as very little time is spent accelerating the ball. Very little time has passed. The ball is still at about 9 meters per second. It has a kinetic energy of 0.25 times 1/2 times 9 squared, which is 10.125 joules. It hits Paul in the face and rebounds at 4.5 meters per second, and the ball now has 2.53 joules of energy, which means it transferred 7.59 joules of energy to Paul's face. As the ball travels, kinetic energy turns into potential gravitational energy as it rises, and reciprocally as it falls back down to the ground.
Chemical energy from the players is transferred to the ball as they exert force on it, which over distance is work. Hitting the ball high up adds more gravitational energy to the equation, maximizing total energy, and thus possible moves on the ball. Newton's third law is seen here. The ball hits on the players as the players hits on the ball. The ball's horizontal momentum is conserved throughout a rally. Even though its velocity might decrease or change, total momentum is conserved as this change is cancelled through reaction on the player's hands. This change in momentum is dependent on the force applied to the ball by the players.
The ball follows a parabolic path with constant horizontal velocity and constant gravitational acceleration of -9 meters per second squared. Because of Newton's first law, the flailing of the players at the ball is useless to alter its path until an actual applied force is made. One can notice that the players tend to launch the ball at angles higher than 45 degrees and only rarely lower than 45 degrees. This is because of the net. Higher degrees get higher vertical displacement to the ball than their complementary angle counterparts. For example, although both 30 and 60 degrees get the same range, 60 degrees gets a much higher y displacement. The world is not perfect. The ball, while in the air, does experience friction, and this friction slows it down tangentially to its path. The energy is conserved, however. It is simply in its dissipated form, as either sound or heat. Although high-speed hits may seem simple, they are challenging. Since kinetic energy depends on velocity squared, hitting a ball 2 times faster requires 4 times more energy. 2 cats are on a roof. Which one falls? The one with the least mew?